So good evening all. Today we'll be starting the week 7 problem solving section of engineering hydrology course. Okay, so in the previous lecture, that is the week 6 lecture, we had started with the surface water hydraulics. That is how the surface water that we already saw what is how the precipitation occurs and how it reaches the land. And once it reaches the land, it gets distributed as surface runoff, and then infiltration also we have seen, and we were focusing on the surface flow part. And so today, basically in this lecture, we'll be continuing the surface flow, and basically we'll be looking into the measurements of the surface flow, and also we'll be looking into how we represent the surface flow. Okay. So before I start, I will give a brief introduction of myself. I'm Akhil. I am currently doing my PhD in IIT Delhi. I am currently in my fourth year, and I have done my bachelor's from NIT Calicut. My bachelor's is in civil engineering, and I have done my master's from IIT Guwahati under supervision of Professor Srija Pekat. And currently, I am enrolled in for PhD in IIT Delhi from the year 2022 under Professor Denny. So we'll start with the section. So before we, so those who have attended my session, they would be knowing we will be following the pattern that we are following is we'll start with two parts. Part A is the MCQ part, which will be having the six multiple choice questions that will be basically covering the entire theory parts of the lecture that has been taken in the last week, and followed by the NAT, that is the numerical answer type questions that will be having the numeric that will be solving similar questions that have been discussed in the class, and also the ones similar numericals on the concept that has been taken, and also it will be helpful for you while solving the assignments, and also it will be helpful to get a practice for solving such numerical questions. Okay. So before I start with the MCQ questions, I will give a brief introduction about the surface water flow. So this we have already seen in the previous lecture. This is just like a recap. So what we're dealing is with is surface water flow, or it is also called direct runoff. So this is you already know we are dealing with surface water flow, and it is also commonly called direct runoff. So basically, surface water flow is that part of precipitation that moves through the so when the precipitation falls over a catchment. So I hope you already know what is a catchment is. We have taken it multiple times in our lectures. Or if anyone is new, you can go back to the lectures. We have taken in detail what is a catchment, and so the precipitation that falls on the catchment get uh, divided or distributed into different parts. Like some scores has infiltration, some scores has and some goes like for satisfying the storages like depression storages, interception storages. These all are filled, and whatever is left, the once the surface starts ponding and it flows starts to form the overland flow, and these overland flows, that overland flow is nothing but once the ponding occurs of water because of the topographical slopes, it starts flowing. It is similar to a sheet flow where a sheet of water, like uniform sheet of water, is moving. And finally, the sheet flows when more and more ponding occurs, they flows and reaches the streams. And when they reaches the streams, so small channels, the flow becomes more narrower, and finally the channel flows are also is called the stream flows, or it is also called the surface water flows, and finally it reaches the catchment outlet. This is what a surface water flow mainly is. So it is basically a part of precipitation. It is not only precipitation, right? It can be other drainage waters on the basins. So one of the water that falls on the basin or the catchment is precipitation, and it can be any other water that drains on the basins, right? And other drainage water that moves through the network of channels. So this I already explained, right? So the water that is falling on the catchment that will be forming as a first the overland flow will be created that we have already seen the previous lecture. And once the overland flows is created, they will be flowing to the streams and they will be flowing as a sheet flow and it will be meeting the streams and the stream flow will be formed, right? And it will basically will once the it reaches the streams, its thickness narrows and basically it forms a network of streams or network of channels. And finally, what it does is drains to the basin outlet, drains to the basin outlet, or it is called the catchment outlet, right? So the another thing to note is this surface water flow is not just the overland flow that is reaching the streams or forming the network of streams. Basically, this is a combination of we know the surface flow is there or surface flow, surface water flow, or we can say the direct runoff, that is the total direct runoff of the basin. That is the total direct runoff of the basin is nothing but the total water that is reaching the basin outlet, right? So it is a contribution of surface flow that we already know that we just discussed how the surface flow forms a network of channel and finally reaches the basin outlet. And there will be interflow, or it is also called subsurface flow, right? And we have the groundwater flow, and it is also called the base flow. So these all will be contributing to the streams, right? Not only the overland flow that reaches the streams, but also all these components, the subsurface flow, the groundwater flow, all these will be contributing to the direct runoff or the stream flow or the surface water flow. The surface water flow, in a way we can say the overland flow is the surface water flow, but the stream flow that occurs, or the total direct runoff that occurs, or the water that flows to the streams, the contribution of the surface water flow interflow, the subsurface flow, groundwater flow, and also the precipitation that falls on the streams, right? That falls on the streams, that falls directly on the streams, right? So basically, precipitation without falling in any location, if there will be some contribution of precipitation that is directly falling on the streams, right? That is also contribution to the direct runoff of the basin. Okay, so this is what we will be looking into. We need all these components. Basically, the contribution of groundwater flow, like a base flow, is a major contribution for stream flows. Like you would have observed when there is no rainfall happening, also in the dry period or the lean period, also we can see some rivers still flowing. So these flows are maintained by the flows like the contribution by groundwater flow and all. And when precipitation occurs, we have to get the additional contribution by the precipitation that falls directly on the streams and also the surface water flow that is flowing due to the runoff that is generated due to precipitation. And also interflow also comes into picture when there is a precipitation or storm occurring, right? The water gets infiltrated in the unsaturated zone and the unsaturated zone, the flow will occur along the topography finally reaching the streams, right? So you have to understand the importance of the groundwater flow, that is the base flow, that keeps the streams still running even during the lean period or the dry periods. Okay, so this is what a stream flow is. We already saw surface water flow is. It is can be overland flow and a stream flow, a combination of that. We know how the we already saw how the overland flow comes. We solved the tried to model the overland flow, and also we tried to model the surface water flows also. Now we will be coming to how we can measure this, right? So precipitation, we saw how we can measure the precipitation. We were using rain gauges, right? Different types of rain gauges also we have discussed. And when we come to the evaporation, we saw how we can measure evaporation, like using evaporation fans or evaporimeters. And when we came to infiltration also, we saw how we can measure infiltration. That is explained in the field, we can make use of the single ring or double ring infiltrometer, and in the lab you can actually have the sample. We can make use of the mini disc infiltrometer. So similarly, we'll be seeing in the surface water case what are the different instruments can be used or the methods that can be used to measure our surface water flow. Okay, so we'll come to surface water flow measurements. This is the main one of the main topics that we'll be discussing today. So first of all, we can look into the unit, how the surface water flow is measured. It is measured in the unit of discharge. So it is measured as discharge. So now, as of now, you will be knowing what a discharge is. Discharge is nothing but volume of water flowing per time, right? So the unit will be in meter cube per second, volumetric flow per time. So this is how we express or we represent, measure stream flow. But the problem is if we try to directly measure this, if we try to directly measure the volume of water that is flowing through a cross section of the or under a cross section of the stream at a particular time, it is very difficult and time consuming, right? So what we have been doing that as an alternative is we are using a easier method, that is by measure. We instead of measuring the discharge, what we do, we measure the stage. Stage is nothing but level. So we measure stage, that is one is stage we measure, and then the second thing is once we measure the stage, we have the different elevations of the water, and if we have the cross section, once we measure the stage, and so we'll be basically with that is the different elevations of the water, and if we have that, and then using that, uh, once the stage is measured, we can measure the velocity. So one is stage, and second we can measure the velocity. So velocity, that is in meter per second, velocity can be measured. So we measure the stages and we measure the velocity. And if we have the area of cross section from this stage, we can basically get the area of cross section. So if we have the area and the velocity at a particular depth or point of consideration, we multiply that, we'll be getting discharge, right? So that is the indirect method. So basic indirect method that we are going to use. So basically, there are two steps. So to be more precise, first step, the discharge of stream is related to the stage using a series of measurements. So what we do is we measure the stage and compute the discharge. Like for a particular station, we take consider a particular station, we make different stage measurements and we calculate the discharge, and then we make a relationship between these two, like a stage versus discharge relationship. So this relationship is called rating curve. So at particular gauging station, so this particular the measuring the stage is also called gauging. So these are called gauging station. That process is called gauging. That is how we measuring the water, different water levels at different time. That is called gauging. And once we measure the stages, we compute the discharge. Once we compute the discharge for different stages, we make a curve that is called the rating curve for that particular gauging station. And once this rating curves are defined, then what we'll be doing is whenever we measure, the stages will be measured at frequent intervals. So once we have the rating curve with us, we'll be measuring the stage at frequent intervals. And whenever we have a particular value of stage from the rating curve, we'll be getting the discharge. So we don't need to calculate the discharge each time. From the rating curve, we'll be getting the discharge uh, for that particular gauging station. So that is our step two. So basically, the water level, or it is also called stage, is observed routinely. So in regular intervals, we measure this, and then using the rating curve, we uh, calculate the discharge. So this is the step mechanism or the method that we use to measure discharge instead of measuring discharge directly. So we just have to measure the stage. We already have the rating curves with us, so we just measure the stage and put it in the graph to get the discharge, right? So so how? So this is the step that we need to follow. Okay, so if we have a gauging stations, the main step followed is these two. If a defined gauging station is there, you don't have to do any other step like try to measure the velocity and all. We just have to measure the stage and directly put in the rating curve to get the discharge value, right? And so next we need to see how this particular rating curves are formed. So rating curve is a curve of discharge versus stage, right? So how the stage can be used to calculate how the stage discharge relations can be made. That is basically how the rating curves can be made, right? So for that we will be making use of the continuity equation, right? So the continuity equation, so the continuity equation here is nothing but discharge is nothing but velocity into area, right? So A is the area of cross section and V is the average velocity. So to make the rating curve or to get the relationship between the discharge and the stage, what we need to do, we have to calculate the area of cross section from the measured stage measurements, and we need to measure the velocity, that is the average velocity. If we have these two quantities for a particular stage, we can have the uh, we can basically have the what we say the discharge values, right? So two things important to us is how to uh, how to calculate the area of cross section using the stage values, and how to calculate the velocity. Here we'll be basically not calculating, we'll be measuring velocity using different types of direct and indirect method. How to measure velocity. So these are the new two tasks. If we have these both, we can directly put this in the continuity equation to get the discharge. So we need two things. One is the area of cross section, other is the average velocity. Okay. So now we can come to the first question. So the first question is, uh, what is the standard method for determining the average velocity? So here we are trying to make a rating curve. So we need to find the average velocity, right? We need the average velocity and we need the area cross section. Then we can find the discharge, right? So to find the average velocity in a moderately deep stream that is typically greater than 3 meters. So the streams which are typically greater than 3-meter depth using a current meter. So what is the how these vertical velocities are measured? Okay, so this is the question. So basically, this is related to measurement of the average velocity, and the instrument that we are using is current meter that you already know. We have seen in the previous week lectures. If you have gone through, ma'am has explained clearly what is the current meter, what are the different types of current meter, and the principle of working of a current meter. So further, we'll be seeing some parts of that in the lecture. So current meter is the instrument that is used to measure the velocity at a particular depth, right? So if we have a deep stream that of a tip that is typically greater than 3 meter, how we can measure the average velocity? That is at what depth we will be getting the average velocity. Okay, so these are the options. So we can I will just give a brief about this. So the problem with the measurement of velocity is that the velocity distribution. So if we see the velocity distribution in vertical direction. So in the vertical direction, the velocity is not uniform, right? So that is, it is not at all uniform. It's not uniform. So if it was uniform, we could have taken that one any depth. If at any depth the velocity remains constant, then we need that particular value, or we can that or there is a clear pattern in which the like it is linear or something, then also we could have got a clear average velocity value, right? So here the vertical profile will be not uniform. So it is not uniform in the vertical direction, also in the also along the width, right? So the velocity will be changing in the depth direction and also in the width direction. So it is not uniform. So that is one problem that we are having. The another issue and how the velocity will be distributed is greatest the greatest velocity will be at the surface, right? At the surface, the greatest velocity will be at the water surface, and the uh, so it will be at the water surface. So vertically, if we say it will be at the water surface. So water surface, and horizontally, if we say it will be at and horizontally in the deepest part. So you understood that, right? So vertically, if we see, the maximum velocity will be along the surface, and the minimum will be at the bottommost part, right? And horizontally, if we see, the maximum velocity will be that particular location where we have the maximum depth. Okay, so that is the vertical. Uh, and if we look on the vertical profile or vertical velocity distribution, vertical profile or vertical velocity distribution, it is somewhat coming to be logarithmic in nature. So it will be logarithmic Hmm? Nature. It is not linear and all. It is not uniform. It is logarithmic. So in fluid mechanics or in the open channel hydraulics, we have already seen, you would have already seen how we measure the average velocity for such a case. So there are two ways to calculate this. So to calculate average velocity in such case, so case one, that is for shallow streams, that is depth is less than 3 meter. There, the average velocity is nothing but the velocity corresponding to a depth of 0 0.6. So V 0.6 is the velocity at 0 0.6 times depth of flow, right? So if the depth of flow is D is the depth of flow, D into 0 0.6 times. So this value, at this value, the velocity will be maximum. Okay, velocity will be not maximum. Velocity we will consider the average velocity. Maximum velocity will be at the surface, right? So the average velocity, if the for a shallow stream that is d less than 3 meter, it will be considered the velocity at a depth of 0.6 times the total depth. And for case 2, that is for deep streams, that is depth greater than 3 meter, the average velocity will be equal to the average of the velocities at v point 0.8 and v point 0.2 by 2 by 2 because it is average, right? So the average velocity in case of deep streams, we'll be measuring the velocity at a depth of zero point 0.2 times depth and zero point 0.8 times depth. These measurements we'll be measuring and we'll be taking the average. So that is the way to measure get the average velocity for a flow in which the flow is non-uniform in the vertical profile with open channel flow with the velocity profile being logarithmic. Okay, so formula is v point 0.8 plus v point 0.2 by 2. So now we can come to our options. So in this question, it has been asked about the uh, it has been asked about the deep streams because typically greater than 3 meters given. And a modulated deep stream they're asking. Measure the velocity at zero point 0.6 depth from the surface. So this is basically, so it is from the surface, right? So whatever the depth I'm saying, that is zero point 0.2 times d or zero point 0.8 times d or zero point 0.6 times d, these all are measured from the surface, okay? It is not from the bottom. You have to make that clear that if it is measured from the bottom, it will be different. The zero point 0.6 times d means the zero point 0.6 into the total depth measured from the top or the surface. The first option is wrong because it is the case for shallow. If it was a case question was for a shallow, this was the answer, right? Taking the arithmetic mean of velocity measured at zero point 0.2 and zero point 0.8 times the depth from the surface. Yes, that is what we just saw. Second option is correct. Third is measuring the velocity directly at the surface and applying reduction coefficient. No. So velocity at the surface will be maximum, right? Measuring the velocity, averaging the velocity measured at the surface and the stream bed. No. This is also wrong. So the correct answer is if it for a deep stream, we have to take the arithmetic mean of velocities measured at a depth of zero point 0.2 times or and zero point 0.8 times the depth from the surface. Okay. So if the question was for a shallow stream, then we just have to measure zero point 0.6 at a depth of zero point 0.6 times the total depth from the surface. So that is done. Just a minute. Hmm. So we can move on to the second question. That is, this is also a method to find the discharge. That is indirect method. So one is to measures, the one that we already discussed, that is by measuring the velocity and by measuring the velocity, we'll be getting the discharge using the continuity equation, and we'll be making the relations of the stage discharge relationship and making the rating curves. Right. So similarly, we can get measure the discharges using another technique without measuring the going to measure the velocities using the current meter. There are indirect methods that can be used to measure the discharge. And also at that same time, if we have the stage measurement, we can make the rating curves also, right? Using these. So this is another method. Without measuring the velocity, we can directly for that is called the dilution technique, or it is a chemical based method. Chemical method is also called chemical method. That is dilution technique or chemical method. It is highly recommended for measuring discharge in which of the following specific conditions. So it is asking it at in which of the following conditions this is recommended. Okay, so will just see the what this chemical, what is the principle behind this chemical method or the dilution technique is. So it is called dilution technique. So basically, what we are using here, we'll be using tracers. It is called these chemicals that are called tracers. So we will be using tracers or chemicals. So tracers or chemicals, tracers are nothing but chemicals that are added to this water to trace their path, right? Trace the path, right? So we'll be injecting these tracers. So tracers will be injected injected to the streams at a constant rate. It will be injected to the streams at constant rate. So that particular constant rate is small q, that is small q meter cube per second. So this is the rate at which we are injecting the traces, and it has the and with a concentration. So the concentration of the trace that we are injecting is C1. Okay. So two things. The trace is injected at a flow constant rate of Q, that is a flow rate, and also the concentration is small q, and the concentration is C1. Okay. And that is one thing to note. And the another thing is the flow rate of the stream, right? So flow rate of the stream is equal to capital Q. So this is what we need to measure, right? We are trying to measure the flow rate. So assuming that the flow rate of the stream is capital Q, and and the initial concentration of tracer in stream. So these tracers are nothing but they are some chemicals, some sort of chemicals, right? So there can be a chance that already in the stream that some concentration was already there. So that we are taking it as C naught. C naught is the concentration of the chemical that was already there within the streams. Right. So these tracers can be something like a sodium dichromate or radioactive chemicals. So these are the common chemicals that are being used as tracers. So these concentrate some, if you say like the stream was already having a C naught concentration of the sodium dichromate or any other radioactive chemical. Right. So that is C naught. And then due to the turbulence, if there is enough turbulence, it will mix well. It will mix well with the stream water. and at the downstream point, and at the downstream point, we measure the concentration. We measure the concentration, and that we are getting it as C2. So all the terms are clear. Small q is the flow rate of the injection. C1 is the concentration at injection. Q is the flow rate of the stream flow. C naught is the initial concentration of tracer already there in the stream. C2 is the concentration of the tracer in the stream at the downstream after mixing with the stream. Okay, now we will be basically applying the continuity equation. So when we apply the continuity equation, so it will be around like Q, that is the small q, that is the flow rate of the tracer into concentration of the tracer plus capital Q, that is the flow rate of the river plus C naught, that is the concentration of the tracer in the initially is equal to at the downstream the flow rate will be Q plus capital Q plus small q into C2, that is the concentration. So if you simplify this and take q out, we'll be getting q will be equal to small q into C1 minus C2 divided by C2 minus C naught. So this is the expression for the discharge using the continuity equation. So if we have the concentration injection concentration of the tracer, out downstream concentration of the tracer and the initial of concentration tracer, and at the flow rate at which the injection is given, then we can measure the discharge using this particular formula. And usually this C naught will be very small. C naught will be very small, very small compared to C2. So what we will neglect C naught and we can simplify this equation as Q is equal to small q into C1 by C2, that is the ratio of initial and final concentration divided minus 1. So this is the simplified equation. So using this equation, we can directly find the discharge. And if we measure different stages of the river at that particular point, we can make the rating curve, and we don't have to repeat this tracer experiment again and again. We can directly, if we know the stage from the rating curve already developed, we can get to know the discharge value, right? So now we can go back to the question. So this is the dilation technique that is already clear. It is highly recommended for measuring discharge in the following specified channel condition. So this is, as you already know, this is a indirect method. So this won't be that much accurate compared to the directly measuring the stage and cross section and applying the continuity equation of finding this and finding the velocity and applying the continuity equation. Right. So there will be these will be used only in the worst case where we cannot keep the where we cannot make use of the current meter to make the velocity measurements, right? Or if the flows are very much turbulent, or like it is very difficult to reach out the river because it comes in between mountains and all. If accessing is difficult, or it is difficult to measure the velocity with the help of instruments like current meter. So these current meters are basically they are like hang like a suspension, right? So there has to be some hydraulic structure above which they can be hanged and to measure the velocity. So that we already know from the previous lecture. So such hydraulic structures are not possible to be built because of the terrain like mountain terrains or mountain streams. Such cases we will be only going for this indirect method. Okay. So we can see the option. At what locations we use this? That is the question. Large, slow-moving river with uniform cross-section. If it's a uniform cross-section and large, slow-moving river, we don't need not do these experiments, right? We just can use what we say uh, a current meter, and we can measure the depth at different different cross section or at along the width we can measure the depth. We can directly, if it is uniform cross section, the depth won't be changing, right? Right. So we can directly, there is no need of to you go for a dilution technique. So that is wrong. Second one is small, highly turbulent mountain terrains. Right. So here, in the first case, slow-moving rivers, the mix, if we use this tracer technique, na, then they won't be mixing properly. This tracers has to get mixed with the water flow, and it has to, after mixing, only we can, if it, given that it mixes properly, then only we can apply this continuity equation. Right. So that will be also a problem if we are using this for a slow-moving stream. So if we are using for a small turbulent stream in mountain streams, that is not turbulent mountain streams, there we cannot access or we cannot measure the velocity with the help of a current meter, or if there is good turbulence so that the water, the chemicals or the traces get mixed properly, then it is in such cases we can use it, right? The second is the right option, option B. Wide streams with the tidal influence. So it is there also we cannot use this, right? And fourth one is canals with low bed slope. No. So we'll be using this. If you want to use it, it will be turbulent and it should be small and it should be in a locations where it is difficult to measure the velocity with the help of a current meter. So I hope this theory is clear about the dilution technique so that we have covered. Now we can move on to the next problem. That is question 3. So that is, which of the segment of the stream flow hydrograph is primarily controlled by the physical characteristics of river basins, the slope, size, and shape, size, and slope, that is the basin or the catchment characteristics rather than the storm characteristics. So basically here we need to look into the concept of stream flow hydrograph. So this is the second part of the second one most the second important or the major concept that was taken in the previous week lecture. That was first was the measurement of the stream flow that we are looking into different methods, and the second was how we represent the stream flow. Okay, so we can go through the quickly go through the theory of this. So basically, we represent how we represent stream flow. Representation of stream flow. So rainfall, in the case of rainfall, we can represent them using with the help, we can represent by plotting the intensity of rainfall versus time. That was called hydrograph, right? So we were plotting intensities and we were plotting different different time intervals. So that was discrete, and we were making use of bar chart, right? And in case of a stream flow, we'll be having a continuous curve because the stream flow or the runoff is continuous. With time, it is continuously, we are getting some of the other values we are getting with time, right? So in such case, we'll be making a plot of we'll be measuring the discharge at the outlet of so we have a catchment. So basically, we show a catchment in this way and shaped catchment. So we have different orders of streams that we already saw in the previous lecture. Right. So this is the outlet point. So when a precipitation happens, the water, overflow or water is used to satisfy all the storage components. Once all those storage components are satisfied, it starts slowly flowing, starts slowly ponding over the surface. When the ponding size increases, ponding depth increases, sheet flow starts. This sheet flow is called the overland flow, and the sheet flows will flows to the channel, and these channels are called in it forms a network of channels and finally come to the stream flow will be formed and finally reaches the basin outlet, right? So at this outlet point, if you measure, so if this outlet point is gauged, and if you measure the stages, and we use the infield current meter, and if we measure the discharge for different time interval, for different time, then we'll be plotting this graph like uh, this is time and this is discharge. So when a storm occurs, so basically this is being plotted for in the case of a storm occurring, if a precipitation is occurring. So initially, there won't be at this limb, there won't be any flow, as there is no precipitation occurring. So this is basically, I already told you when we started, in the dry period, some flow is maintained in the river that is due to the nothing but the groundwater flow or the base flow. So this is the base flow contribution, or this particular AB is called base flow recession, base flow recession. And from the B point, the direct runoff starts. That is the runoff rainfall. The runoff starts, water starts reaching at the point, this point. That is, water starts reaching at this point, that is the outlet of the stream. And it increases and goes on and becomes a peak. So there are different points here, C, and the maximum point is P, that is peak. Then we have in the recession, we have a point D, and finally it reaches a point C, A, B, C, D, E, and then here at point E, the that is at this particular point E, the runoff or the entire water has reached this point. Now no more water contribution will be there from the storm, and whatever water is still coming will be due to base flow, similar to the initial case, initial before the stream case, before the storm case, right? So we can now plot what are each of the points. So AB we know it is a base flow recession. BC is called the rising limb. Rising limb is nothing but more and more water have started reaching the outlet point. So this outlet point I'm calling it as O. So more and more water has reached O, and at times progresses more water will be reaching. And P is called peak. That is a maximum runoff it has reached. A maximum uh, water discharge, the rate of flow that is occurring at the point O is called maximum rate of water that is flowing at the uh, flowing at the outlet point is called uh, O. At the outlet point O, that particular point is whatever the discharge is, that is called peak P. And this particular area, that is CPD, that is called the crest. CPD is nothing but is called the crest. So, and DE is the opposite of the falling limb, that is called the rising limb, that is the falling limb, right? And finally, and the point D is called the point of inflection. So the starting point of the recession limb. So D is called the point of inflection, inflection or starting point of recession limb or falling limb. Flow is contributed from different storages of the catchment. So here at D to E, the flow is contributed by contribution to different charges and represents the maximum storage, right? So at uh, D to E, the storage is contributed by different storages in the catchment. So the stream has ended. So the runoff ends here. The runoff ends at the point. So runoff ends at what we say at E, and the storm influence ends at T. So once it has reached T, there is no more storm happening. Storm has stopped. So whatever the profile now we are getting, that is the recession limb, a falling limb we are getting, that is solely the property of the catchment. It is only depending on the property of the catchment. It is nothing to do with the storm that is happening. But in case of the rising limb, that is the rising limb BC, it was due to two contributors. One is it depends upon how the catchment is, whether it can store more water or whether it can drain water quickly to the outlet, or it will take some time to reach the outlet, or if more precipitation occurs, the peak will be more, the rising will be at a higher rate. If less precipitation occurs, the rise will be in lower rate. So that was depending on the storm and also the property of the catchment, right? But in the falling limb DE, it is depending only solely on the catchment properties because the storm has already ended, right? So that is why point D is called the point of inflection. That is at that point, the influence is only the profile of the hydrograph, stream flow hydrograph is only governed by the catchment properties. Okay, now we can come back to the question. Which of the segments of the streamflow hydrograph is primarily controlled by the physical characteristics of river basin, such as shape, size, and slope? So they are asking which section of the streamflow hydrograph is characterized by the physical characteristics of the basin alone rather than the storm characteristics. So that we already saw. The answer will be the recession limb or the falling limb, right? The concentration curve or the rising curve. So the rising curve is also called concentration curve, but in the concentration curve, there will be the influence of both the storm, and the catchment properties, right? For different catchment, if it is a band catchment, it will be different. If it is a narrow catchment, it will be different. Narrow shaped catchment will be different. If it is like a W shaped or the eight in the shape of uh, like two ovals connected. If that is the shape of the if that is the catchment width reduces in the middle. In such cases, the rising line will be different. And also, if the storm intensity is high or low, then the rising line will be different. But when we come to the falling limb, the storm has stopped. Only it will depend on the physical characteristics of the catchment. Uh, it decides how the profile will be. Right. So first is storm. The rest of the segment that is also driven by both recession limb, that is the correct answer, and initial base flow curve. So initial base flow curve is independent of both stream flow. It may be indirectly dependent on the storm. That is when more storm happens, the base flow can groundwater discharge increases and the base flow contribution may increase indirectly, right? Otherwise, it is independent of both stream flow and the type of the catchment, right? So the correct answer is the recession limb or the falling limb. Okay, so now we can move to the fourth question. So that is also related to the stream flow hydrograph or the surface water flow representation. So How does a fan-shaped catchment generally alter the resulting hydrograph compared to a fern leaf-shaped catchment? So this is basically they are asking based on the physical property, that the shape of the catchment, how the outlet stream flow hydrographs will be different. So before uh, going to that, so I hope one thing is clear. Basically, a stream flow of a catchment, if they ask stream flow hydrograph of catchment, we are measuring the hydrograph at the outlet point. Okay, we are measuring the hydrograph at the outlet point of the catchment. So that thing you have to remember. So we are taking a case, two cases. One case, a fan shaped means it has a high it has a larger area in the inlet and the outlet in the inlet and the outlet location, almost like a sphere or like a circle, and we have a font shape that is nothing but a narrow uh, catchment, and we have different streams connected to this, right? So these are the outlet points. So now on the basis of this, we can try to predict or may try to have an idea or guess the stream flow hydrographs. So this is for the fan shape, and this will be for the fern leaf shape. So this is the fan shape, and this will be fern leaf shape. Okay. So here, if you could see, we have at the in outlet location, near to the outlet location, we have a large area, right? We are having a larger area near to the outlet location. And also, if we see the distance of the farthest point to the outlet location is also less, because the it is a not short streams. It is not elongated like in the case of a fern leaf shaped streams. So the peak can occur, the water can reach the outlet point quicker. Or the time of concentration, that also we see the concept time of concentration is nothing but the time taken by the water from the farthest point to reach the outlet. So that will be smaller, right? So the time to peak will be high. So this is discharge and this is time. That is stream flow hydrograph we are representing. So the peak will come fast and the rate will be higher, right? So the water that falls and once the runoff is generated, it will be forming very quickly to the, so the flow rate will be high. But in case of a pond shape of a narrow stream, so we can see water are water will be coming from a very large, long location, very long uh, area, very long streams, like so the time of concentration will be more. So the time to peak will be more. And also by the time the water reaches the amount of water reaching, the rate at which the water reaching the streams will be also less. So the peak will be also less and time to peak will be also less. So that we can draw something like this. The peak is also less and time to peak will be also less. Okay, so this is the two different shapes of a fan shape and a narrow catchment. So here they have been asked to compare both. It produces a lower peak flow. So how does a fan shape alter? So the characters of fan shape is given the option. The fan shape and the font shape. It produces a lower peak. Uh, it produces a lower peak flow and a broader base. No, fan shape is producing a higher peak. So this one is wrong. It produces a high peak and narrow base. Yes, it is a high peak and it is having a narrow base. So the second option should be correct. So we can move on to the other options also. It produces a delayed peak with a identical peak magnitude. No, if the peak is not delayed, it is very quick in case of a fan shaped. It only affects the base flow, leaving the direct runoff unchanged. That is wrong. So the correct option is produces a higher peak flow with a narrow base. So with that, we already show here. So the base is narrow compared to this particular base, and also the peak is higher compared to this peak. Okay, so we can move to the next question. Just a minute. Hmm. So the next question is based on a technique that is used to remove the base flow concentration. So you already know we have in the stream flow contribute when we draw the stream flow, we already know initially the contribution before the stream occurs and after the stream recedes. There is a part where it is only driven by base flow, or during the occurrence of the stream also there is a contribution of base flow. So if we want to study the effect or the runoff generated by the stream along, there is a need for us due to remove this base flow contribution, right? So even after the stream or storm is occurring, more and more water base flow may increase, and more and more water will be generated, right? So we need a technique to remove this or to separate this base flow contribution from the actual direct runoff, right? So that we'll be looking into in this particular question. So the method they're asking is, so one method that I'll be discussing in this section will be the straight line method for base flow separation, how the base flow conceptually separated from the direct runoff. So if we have, so one thing that you need to understand, we have the storm hydrograph. So we already saw what is a storm hydrograph. If we subtract the base flow contribution, what we are getting is the direct runoff hydrograph. Direct runoff hydrograph. This is also called DRH. Direct runoff hydrograph or DRH. Okay. So how we can separate this out? That is how what we are going to see. So in case of so that how we can separate this particular technique is called base flow separation techniques, right? So one of this method is straight line method. Okay, so in straight line method, what we'll be doing is the horizontal line is drawn from the point at which the surface runoff begins to intersect with the recession limb. Okay, so the horizontal line is drawn from the point at which surface runoff begins to the intersection with precession limb or falling limb. Right. So basically, if we could draw, if we have a stream hydrograph like this, so initially we have the base flow precession, and then we have the rising limb. So it will be smoothly rising, and then we have the crest, and we have the falling limb, point of inflection, falling limb, and then followed by our base flow recession. So here, what they're saying, this is the point, that is the point B, that is the point at which direct runoff start. This is the point at which runoff starts, right? So we'll be drawing a horizontal line along this point. Okay, so we'll be drawing a horizontal line along this point. So whatever water is there below this, so this particular amount of water, this will be called, taken as the contribution by base flow, and whatever left here, so whatever volume left here, so whatever volume left here, this will be DRH. DRH is nothing but direct runoff hydrograph. So if you, this is the one way of finding, so this intersects the recession limb at this particular point. So this is the point of intersection of the horizontal with the recession limb. Okay, that is the straight line method. So we can see the options now. By extending the pre-storm base flow curve horizontally past the peak, no. By extending the recession curve backwards to the time of flow, no. By joining the beginning of surface runoff directly to the end of the with a straight line. Yes, that is what we just did. And by tracing the line parallel to the rising limb. No. The correct answer is by drawing a horizontal from the point of starting of the direct runoff. Whatever is below that we are taking as base flow, and the remaining one will be our direct runoff hydrograph. Right. So we can move on to the final question in our MCQ type. How does an acoustic Doppler current profiler? So this is a advanced instrument that is used to measure the river discharge. Okay, determine the velocity in a river. So it basically measures the velocity and also the river profile also, that is different at different depths. What is the velocity that we'll be getting, right? So basically this is an instrument. It is called ADCP. So ADCP, this instrument, it is mounted on a boat. So we will be requiring a boat, and the ADCP will be attached to the boat with the help of a string or a rope, we'll be attaching this, and the ADCP can move float in the water. Right, so it has a floating technique that so that it can float on the water and it will be attached to the boat, and the boat will be moving, and we'll be moving from one bank to the other, and then we'll come back to the starting bank, right? So so across the width of the river, we'll be moving, and while moving, we'll be measuring the velocity and the depth. So we'll be getting the different depth of the or the profile of the we'll be getting both the so we need a boat attached to a boat. We will be measuring both velocity and depth along the width. So along the width, we'll be measuring the depth and the velocity. So basically, how it measures is it it transmits sound waves. So sound is transmitted into the water from the surface by the transducer. So basically, sound is transmitted into the water from the surface using the the transducers are there as a part of the ADCP. So it will be transmitting sound waves, and it will be reach to the it will strike the bottom of the river, and it receives the signals are returned back, and it is received by the transducer of the receiver. The change in frequency or the Doppler shift that is measured by ADCP into the and is translated into water velocity. So the change in frequency of the transmitted signals, or this is called Doppler effect or Doppler shift, is measured and it is converted to velocity. So the advantage is that it gives both the profile and also the velocity and the profile, and it takes less time, and discharge measurements can be made during the flooding conditions also. These are some of the advantage. So only thing that you have to remember is we'll need a boat, and we'll be attaching the ADCP with the help of a string or a rope, and we'll be moving from one bank to the other bank. So within the ADCP, we have a transducer that can emit sound signals. So that will be while moving, that will be continuously emitted, and these signals will strike the bottom of the bed, and it comes back and is received back by the transducer, and it will measure the change in frequency, and the change in frequency is called the Doppler shift. This will be measured by the transducer, and uh, they are programmed to convert these Doppler shifts into water velocity. Right. So in this way, we'll be getting the water velocity and also the depth. That is the distance traveled by the signal is will be nothing but the depth. So we'll be getting the profile or the cross-sectional profile of the river, and also the velocity at different depth or along the width. Okay, so we can look into the option now. How does an acoustic Doppler determine the velocity? By measuring by measuring the physical forces of water pulse against the submerged mechanical router? No. By measuring the travel time of the sound pulse to reach the river bottom and return back to the device? That is not the case. We are not measuring the water travel time of the sound. By transmitting sound uh, into the water and measuring the Doppler shift, change in frequency of the return signal. So that is the right answer. By taking single point measurements, so that is wrong. It is not Doppler measurement. So we'll be getting the measurement at any depth, not just point to point 8. Okay, so that is ADCP. These are the advanced instruments that are used to measure the discharge. Uh, so now we can move on to the numerical answer type questions. So the first question is related to the current meter. So we have already seen the what is a current meter, we would have already seen in the previous lectures, and also we know it is used to measure velocity, right? So current meter, it will measure velocity, right? So basically, what a current meter component of a current meter looks like. So it will be having a suspension cable. So it will be suspended from a fixed support. We will be having a cable, and it basically has some sort something like this, an axle, and will be connected to. So this is nothing but we call a vane, right? So this is vane, a vane that is to keep it in the direction or to align it. So we have a vane to align the current meter with the flow direction, right? So we have a vane here, and then this is connected to a rotating cup system. So there is something like this, and inside this we have different cups. This is called cups, and the water is flowing from in this direction. This water current, and these cups will be, and this rotation can be measured here. So here is something to count the revolutions of the cup. So we measure. So basically using this we'll be measuring. So also there is one more part at the bottom, that is a counterbalancing weight. So we have a balancing weight here. So this particular weight will align. So this is called balancing weight to keep it aligned in a particular location, particular fixed in a particular location. That's the balancing weight. So basically, we'll be measuring the number of rotations. So there's this counting mechanism over here. It will be measuring the number of resolutions of these cups, and then each of the current meter will be calibrated with an equation, that is V is equal to A plus Bn, right? So then we find the values. Each of the meter will be given with the value of A and B. So if we have, and here the N is nothing but the speed of the current meter in rotation uh, per second. Okay, and if we substitute this, we have the velocity. Okay, so in this question, a price current meter is used to measure the velocity The calibration equation is, so it is calibrated and the equation is already given, where n is nothing but the number of rotations per second. The velocity in meter per second we have to find if during a field measurement there was 42 revolutions in 60 seconds. So when we uh, kept the current meter in the stream is against the stream flow, the cups rotated 42 times. So the counter meter showed a 42 times of times rotation when we counted for 1 minute. So that is given, and then now we need to find the velocity. So this is a simple question, right? Straightforward. Nothing but first we need to find n. N is nothing but the number of rotations per time. That is total rotations divided by time in seconds. That is equal to total, it rotated 42 times, right? In 60 seconds divided by 60. That will be equal to 0.7 revolutions per second or rotations per second. So now we can substitute n to get the velocity. So velocity, the unit will be, they have mentioned it will be in meter per second. If you substitute it is in, so it will be 0.65 into n is zero point 0.7 plus 0.05 calibration constant. So velocity will be equal to 0.505 meter per second. So this is how we use a calibrated current meter to measure the velocity. So we will be putting it in the against the water current, and we will be measuring or counting the number of rotations of the cups. And once we have that value, we'll be finding n, that is number of rotations per second or the speed of the current meter. Once that is measured, we'll be putting it in the calibration equation that comes along with the specifications of the current meter that we are having. And then if we put those values, we'll be getting the velocity, right? So the velocity is coming out to be 0.505 meter per second. So we can move on to the next question. So this is also the theory we have already seen. So this is related to our dilution technique or the chemical technique. That is a salt solution with a concentration of 600 milligram per liter is injected into a stream at a constant rate of 0.05 meter per second, meter cube per second. The stream backward concentration is 10 milligram per liter. Downstream, the steady state concentration is 25 milligram per liter. Calculate the stream flow discharge in meter cube per second. So, if you remember, we had applied that continuity equation. So, if you remember, the continuity equation was continuity equation. So, we need not by heart the formula, just write the continuity equation, that is Q1, not that is small q into its concentration, that is C1. That is C1 is the concentration of the tracer, and Q is the flow rate of the tracer into the stream, plus Q is the stream flow, and C naught is the concentration that is already there in the stream, is equal to Q plus capital small q into final concentration of C2. So if you simplify this, we'll be getting Q is equal to small q into C1 minus C2 by C2 minus C naught. So this is the equation. So we are not simplifying this because in this question, I think C naught is given. So we can write the given values. So C1 is nothing but that is a concentration of salt solution is 200 milligram per liter, and flow rate of injection is 0.05 meter cube per second. And the background concentration is the concentration that is already there, that is C naught, that is nothing but 10 milligram per liter. And the steady state downstream concentration, that is the final concentration C2, that is equal to 25 milligram per liter. So the stream was having a 10 milligram per liter concentration of NaCl. Then we added 600 milligram per liter at a rate of 0.05 meter cube per second. Then the downstream, the concentration was measured and it was coming out to be 25 milligram per liter. Now using this data, we need to measure the stream flow. So Q is given by small q into C1 minus C2 divided by C2 minus C naught. So we already have all the values. This is substitution. 0.05 into C1 is 600, C2 is 25 divided by C2 is 25 minus C naught is 10. So this will be 0.05. Numerator will be 575 divided by 15. So that will come out around uh, 1.916 meter cube per second. Okay, so this is direct substitution. Only thing, you don't have to by heart the formula, just write the continuity equation. So you know the injection at a rate of Q, so concentration is C1, and the flow is happening at capital Q, and the concentration already there is C naught, that will be equal to, after the mixing, that is downstream, the total flow rate will be Q plus capital Q plus small q, that multiplied by the final concentration will be C2. So if we equate that, we'll be getting the equation for capital Q, right? So the flow rate is 1.96 meter cube per second. So we can move to the next question. So a streamflow hydrograph, so it is related to the streamflow hydrograph, begins to rise at t equal to 2 hours. So the recession or the rising limb starts at t equal to 2 hours. That is the point B that we already discussed. With the initially measured stream flow, that is entirely at this point base flow. That is, we know at that but till that particular point the only contribution is by base flow, right? So that is 15 meter cube per second. The direct runoff ends at t equal to 12 hours. That is the point at which the runoff contribution at the where all the water from the farthest point have reached the outlet. Now no more direct runoff is there. Now the contribution is again only due to base flow. That happens at the time t equal to 12 hours. At which point, and that particular point, the stream flow is 25 meter cube per second. Using the straight line method for base flow separation, calculate the estimate of base flow at t equal to 7 hours. So the method that we just discussed before, it is called the horizontal straight line method. That is, we are drawing a horizontal line connecting these 2 points. So these 2 points are given. The point at which the precision limb starts and the it meets the other point. That two are given, right? So basically, the straight line method interpolates the base flow linearly between the start of the base flow and the end of the runoff point, right? So basically, so this is the, you can draw the retrograph. So initially it is the blissful recession limb and then this till this point. That is, that point is t equal to 2 hour. The inflow has rising has started and the peak has occurred, and at t equal to 12 hours, at this point, it was measured to be 15, and this will decrease till this particular point, and this will be nothing but. So that was the earlier method that we discussed was the horizontal line method, and here the recession limb, the stream direct runoff ends at this particular point. That is nothing but t equal to 12 hours, right? So at this point, the runoff is 25. So straight line method is nothing but so you have to just to draw a straight line between these 2 points. That is the starting and the ending. So this is will be our base flow. This shaded region will be our base flow. So this is how we can estimate our base flow. So they are asking what will be the base flow at t equal to 7 hours. So at t equal to 7 hours, base flow will be this much, right? So this is the value. Q is equal to question mark. So Q B base flow at so what is the base flow contribution at t equal to 7 hours? So we know this is a straight line, and if we draw a triangle like this, it is linear interpolation, right? So if I could draw this particular triangle here, so this is 2, this is 12, and this is 7. And the y we have, this is the unknown that we need to find q. Here it will be 15, here it will be 25. Now we can apply the similar triangle properties, that is similar triangle, this particular smaller triangle and the larger triangle, then we can directly compute, right? So we can write q, that is minus 7, no, q, so this side will be 15, so this will be, this length will be q minus 15. So if it is q, if this is 15, if this, so this value, we are taking it as q, okay, and this is 25, right? So this will be 25 minus 15, that is nothing but that will be equal to 10, and this will be q minus 15. Okay, so set q minus 15 is the side by the horizontal is 7 minus 2 is equal to 25 minus 15, that is 10, divided by 12 minus 2. So if you solve this, q is equal to 25 by 10 by 10, right? 10 by numerator will be 10, denominator is also 10 into 5 plus 15. So this will be 6 plus, so this will be 1, that is 5 plus 15, that will be equal to 20 meter cube. per second. So that is the base flow. So base flow rate at t equal to 7 hours is 20 meter cube per second by straight line. Okay, so we can move on to the next question. So we have three more questions. So in this question, we'll be discussing a new concept, a new indirect method similar to the one of the indirect method that we already saw was the dilution technique, right? This is another technique that can be used to measure the discharge. So that is called the ultrasonic technique. So if two ultrasonic transducers, so it will be basically using of ultrasonic transducer A and B are installed in the opposite banks of the streams to measure the velocity. So what we'll do one thing, first we'll look at the theory once, we'll revise the theory once and then we can go on to the question. So this is ultrasonic method. So flow velocity is used, so it is measured, as the name suggests, it is measured using ultrasonic signals. And next, so I will just explain use it with the help of a figure. So consider two banks. Consider the banks of a river, the bank one and this is the other side. So what we basically doing will be we'll be keeping two transducers A and P in the either sides of the bank and the let the C with so we have ultrasonic signal, so velocity of sound in water, we are taking it as C, so that is the velocity of sound in water. So in this direction flow will be taking place. uh, so the line joining usually these two transducer places that the line joining will be making an angle of theta, so that theta is usually 45 degree. So it will be making an angle theta. So the flow velocity will be in the horizontal direction. So that is what we need to measure. We need to measure, and from the transducer A to transducer B, we'll be sending signals and measuring the travel time. So we'll be sending signals. The velocity will be taking it as VP. So VP is the velocity, and so uh, it will be sending signals to B, and B will be sending signal back to A, right? And we'll be measuring the time, that is T1 time is taken from A to B, and T2 is the time taken from B to A. This we will be measuring, and then the total inclined length of this we will be already knowing because the locations of the transducers are fixed. That is length L, right? So now we can write the equation for T1 and T2. So T1 will be nothing but distance traveled by time, that is L, distance traveled by L, and V will be so from when it travels from A to B, and the one component of this velocity is also in. So this VP is the component parallel is the VP will be equal to V cos theta, right? That is a component parallel to the right. So when it goes from A to B, it is in the direction of that component, right? So it will be C plus V cos theta, and T2 can be measured as L by C minus V cos theta, right? So so we have the relationship for both, and using this, we can come up with a equation for velocity. If we take out the velocity, if we simplify this, we'll be getting this as L by 2 cos theta into 1 by T1 minus 1 by T2. So if you simplify this, we'll be getting a expression for the velocity of flow, given that we have the time taken by the ultrasonic signals to travel from transducer A to transducer B, and also from B to A, and also the inclination angle theta. Usually it is 45 degree, right? So here, another thing you have to note is that the velocity measured, so this is to remember, like the velocity measured in the stream at a height h, that is where the transducers are installed. So we are not measuring the average velocity or the at a particular depth. It is measured the velocity, whatever measure velocity we are getting will be the velocity at that particular height at which the transducers are installed. If so, we won't be getting the average velocity and only the velocity at that particular height where the transducers are installed. Okay, so this is the theory. Now it could be the question. Now we can move on to the question, which will be based most probably at direct substitution only. If we know the theory. So A and B are installed in the opposite sides of the streams. The straight line distance between so that is capital L. So capital L is given as 100 meter. So we can write this down. So L we got it as, so this is the equation we're going to use. L we got it as 100 meter, and then the straight line is 100 meter and joining, making an angle of 60-degree with the direction of the stream flow. So it is making an angle of 60-degree with the direction of stream flow. So with the direction of stream flow, it is making an angle of 60-degree. So theta is what that is given. So theta is 60-degree. So we can write that down. Theta is equal to 60-degree. And the direction, with the direction of the ultrasonic signal was sent from transmitter and receiver P downstream at with a travel time of, so the travel time is given as 0.60675 seconds, and the reverse was 0.0676 seconds. Calculate the stream fluid velocity at the height where the transducer is installed in meter per second. So T1 and T2 is also given. T1 is nothing but 0.0675 seconds, and T2 is 0.0676 seconds. Okay, now it is straightforward, just substitution. Velocity is 100 meter divided by, here also there is no need of by hearting the equation, you just have to write this relation. So T1 and T2, you know the relation, right? So this is only distance by time. So distance by velocity is time. That is the only equation that you have to remember. And the velocity you already know the relative, how to calculate the relative velocities, right? And so 2 into cos 60-degree divided by 1 by T1 is 0.0675 minus 1 by 0.0676. So if you solve this, it will be coming around 2.191 meter per second. So if you solve this particular equation, you can check it will be coming around 2.191 meter per second. Okay, that is how we measure the velocity using ultrasonic method. We have two banks, we have the transducer installed. We will be sending the signal, ultrasonic signals from one side to the other side, right? And we will be measuring the time taken. So we can move on to the second last question. So this is something related to the midsection formula. So that is a technique used to find get the total discharge if we have the different stages. We have different stages and the velocity measured at different stages. We can make use of the midpoint midsection method to find the discharge, right? So in a stream gauging operation using midsection method, midsection method. The data is collected at a specific interval I, vertical interval. So different interval I data are collected. The depth at I is vertical I is 2 meter. That is at a I is 2 meter, and the mean velocity at is either. So at I, di is 2 meter and velocity vi is zero point 0.8 meter per second. The horizontal distance from the initial point to the bank to the previous vertical is 10 meter. So the horizontal distance of the initial point on the bank to the previous vertical is 10 meter, and the distance to the next vertical. So the horizontal distance from from the bank uh, to the initial point on, so this is the initial point on the plank I equal to 0. Then this is the current point I. So, or I can write it as I minus 1. And from the current and the distance to the next is 16. This is I plus 1. So this is 16 and this is 10. So this is, we can call it, this is the width I minus 1 and this is the width I plus 1, right? There are two width at I, and we have the depth uh, depth at I d I we have as 2 meter and vi we has as zero point 0.8 meter per second. So this is the data given with, or both the width are also given. That is 10 meter and 16 meter. So using all this data, we need to find the discharge, right? So discharge at to this element. So the horizontal distance is, so this is we already taken considered. So it's 10 meter and 16 meter. Calculate the partial discharge assigned to the vertical I. So this particular vertical, so this particular vertical I. So this is a portion of the circle. So similarly, we will be dividing our entire cross section into number of verticals. So this is the how they are asking to find at this particular vertical what will be the elemental recharge or the recharge contribution, discharge contribution. So delta we can represent it as delta Qi that we need to find. So delta Qi is nothing but Vi, that is the velocity, into Di, that is the depth, or Di or Vi, depth, into the average width at that particular vertical. So here Vi into Di into Wi we can write as the average width is in the left it is 10 meter, in the right is a 16 meters. The average width would be 10 plus 16 by 2, right? No, the average width will be 10 minus, not the resultant width will be 10 minus 16 by 2. So that will be 10 by 2 minus 16 by 2, right? So this particular width, that is 10 by 2 and 16 by 2, 8. So that will be equal to Wi plus 1 minus Wi minus 1 by 2. That will be Vi is 0.8 into Di is 2 meter and Wi is 16 minus 10 by 2. That is 8 minus 5. That is 3 meter, right? Uh, 3 meter is the width corresponding to this particular vertical. Okay, it's equal to 0.8 into 2 into 3. That is equal to 4.80 meter cube per second. So that is how we find the velocity corresponding to the discharge corresponding to a vertical eye if we have the width before and after. Okay, so now we can move on to the final question. So at a known distance from the initial point of the stream bank, the measured depth of the velocity of the stream are shown depth and velocity. So depth and velocity at different points from the uh, stream bank is shown in the table. Calculate the discharge at that location. So we are given with the measurement of distance uh, that is there at different locations. The distance we are given from the initial location, the depth and the mean velocity is given at 4 from 4 at the bank, what it is at 12 meter, then the depth is 3.1 meter velocity. So these values are given. We need to find the what we say, we need to find the discharge, total discharge that is taking place. So for this, Uh, first of all, since the distance are given cumulatively, that is from the end, we can find the delta W. We need the elemental width so that we can get the elemental discharge and take the summation. So we will be doing that. So we need the width delta W, right? So can extend it here itself. Okay, so delta W will be the first case, the width is 0 and 12, right? So 0 minus 12 by 2, that will be 6. And second, it is 32 and 12, right? So so in that case, we have for delta, so delta W1 was nothing but we had, so we'll be using this particular equation, that is For the first case, we will be using particularly 12 minus 0 by 2. This is similar to just what we already did in the previous question, right? That is 6 meter. So delta W2 also I'll be showing. So this has two parts, one in the left and one in the right, right? So that will be, so we know after in the I3 it is 32, 32 minus 12 by 2. So 32 minus 12 by 2, and to the left we have 12 minus 0 by 2, right? So that will be equal to 16 feet. So this is how we will be finding for the intermediate section, that is 32 minus 12 by 2 and 12 minus 0 by 2, and the summation of that will be 16. Similarly, in the next case, we have this is 32, that is 52 minus 32 by 2 plus 32 minus 12 by 2. So here also delta W3 will be showing. You can show one more sample calculation, delta W3, that will be 52 minus 32 by 2 plus 32 minus 12 by 2, right? So can solve this. It will be coming around 20. Okay, so rest I'm not solving. So it will be around x is 20. The other one is also 20. This is also 20. And this is also 20, 20, 20, and 17.5, 15, 15. So you can calculate this with the help of Excel if you want. Then 11.5. So in the end, it is 3.2 and 0. So the width are 325 minus 3117. The width is equal to 4 meter. That is 325 minus 317 is 8 by 2 will be 4 meter, right? So we got delta W. So we got the width of each of the section. So once we have the width, we also have the depth and velocity is also given. Then we just have to calculate velocity into depth into delta W, like in the previous question. This will be giving us each of the elemental discharge. So if you do that calculation, it will be coming out to be 0, 18.4, 76.6, 100.3, 152.8, 63.9, 76.9, 153.4, 216.7, 193.1, 6 to 34.1, 280.8, and so on. So we just have to multiply all these three, 1, 2, and 3. So we have all the values as multiplication. Similarly, it will be 0 multiplied by 4, it will be 0. And so these are nothing but delta Q. So total discharge Q will be nothing but the summation of delta Q that will be coming out to be 3061.4 meter cube per second. So in such questions, only thing is we have to be careful while finding the width. So the width at the end banks at the first section, the last section will be different and compared to the width. So the first section, last section width will be the wi plus 1 minus wi minus 1 by 2. So it has only in the one side, the other side it is not there. If it has in both sides, there will be W2 minus W. Uh, it will be Wi plus 1 minus. So this is Wi plus 1 minus Wi by 2 plus Wi minus 1, Wi minus Wi minus 1 by 2. Right. So that is the way we need to find the delta W's for each of the sections, and then we can multiply it with velocity and depth to get the discharge for the elemental discharges. And if you uh, add it, then we will be getting the total discharge. So if you, so I will just complete this. So we will be having 280.8 and 288.6 to 83.0 to 20.3. So I'm continuing it here to 20.3, then 191.9, 168.3, 84.8, and 43.4, then followed by 0. Okay, so this is also a part. These four are also a part of this, and followed by finally followed by 0. Okay. So you can check the final answer should be coming around 3061.4 meter cube. It is not meter cube per second. The units are given in feet, right? So it won't be meter cube. So from the value itself, we can, so if it is meter, it is very large value. So it will be around this much CFS, right? Cubic feet per second, CFS. So I'm stopping here. So if you have any doubt in this particular section or any of the questions, or if you have any doubt in the assignment questions or any of the uh, any questions that you find it difficult in any of the standard test books, you can write it to me. Uh, my name is Akil J and my email ID is Akil AKJLJNANADEVAN at gmail.com. So I'm closing here. Thank you for joining.